All right, people. I believe all of you are doing great, having a good time. So, welcome to this session that is wave optics. Welcome to the session that is wave optics. Okay, just a second. Let me fix up everything over here. So, guys, let me know in the chats if I'm perfectly audible, visible to each and every single student. I would want you guys to tell me in the chat. Everybody. So today we'll have to finish this session. That is what we call we say over here, wave optics, okay? And in the next marathon, I'm going to start your class 11. So be ready for that. Okay, we'll start from the scratch. We'll start from the basic mathematics itself. And I would want you guys to smash the like button if you have not liked the session yet. Okay? Mark the attendance because marking the attendance is extremely mandatory. So guys, in the today's session, we'll have to complete the wave optics. Okay, it'll just take us 4 to 5 hours. It's not that big. It is a small chapter. We'll have to finish it in a very less amount of time, and I'll be showing you every single concept and every single problem we'll be solving in the session itself. Okay, semiconductors I'll come up with like after a few days, but the next marathon I am starting with the class 11th chapters. Okay, because a lot of students have been commenting in every single session, sir, please start the 11th. You haven't started now. So that's why I will be starting the class 11th, and in between I'll come up with the semiconductors also, so you don't have to worry about anything. That's my job. I'll do that. So chill. So we'll have to talk about the wave optics. Okay, previously we are done with the ray optics. Now we need to talk about the wave optics. Okay, again I'm telling you, and let the people come and join, and guys, smash the like button, everybody out there. Okay, so let's dive into the session. Let's discuss all the things over here. Guys, understand one thing very carefully. Let's suppose when it comes to the wave optics, before that, let's talk about a light. Let's talk about light. What light is all about? It will just take me 2 minutes, okay? So guys, the very first thing over here is, that is, if I say the simple question to you guys, let's suppose when it comes to the light, is this light a particle or this light a wave? Okay, this was the biggest question back in time. Lot of physicists used to basically fight with each other on this particular issue. Is this light a particle or this light is a wave? We have discussed this previously. Okay, we say light has got dual nature. Okay, we say light has got dual nature. Now my dear friends, when this controversy started back in time, we say the first physicist, his name was Newton. He came up with the corpuscle theory of light. This corpuscle theory was basically saying, when it comes to the light, it was saying light is a particle. Light is a particle. Okay. According to this corpuscle theory, we say light is a particle. Light is made up of small tiny particles called the corpuscles. This was the theory given by the Newton at that point of time, and everybody accepted this theory. Why? Because Newton was having the big name. He was a big scientist, big physicist. That's why it was widely accepted at that point of time. And then comes the Huygens. Okay, and we say this Huygens said light is a wave. Light is a wave. Light is a wave. According to the Huygens basically said light is a wave. Even he said light is a mechanical wave. Okay. Now guys, what was the strong proof that clearly proved light is a wave? This, if you have got a light source over here, okay, you say, sir, it is light, it is wave coming out of this light source. What was the strong proof? This also we have discussed, that is YDAC. Guys, what I'm saying is that back in time, there was a question that is this light a particle or the light is wave? So different number of physicists came and they gave the theories. The first one was Newton. He came up with the corpuscle theory. He said that light is a particle with the help of this theory. We don't have to go into this. Okay, what does it say actually? Simply, light is a particle according to this theory. Then comes the Huygens wave theory. It says light is a wave, mechanical wave, but this was not accepted. Why? Because Huygens was not that big scientist at that point of time as compared to the Newton. But later on, when this Young's double slit experiment was performed, this is what we need to understand, learn in this chapter. This clearly proved the wave nature of light. Proved wave nature of light. Wave nature of light. Okay. And later on, we have discussed about the photoelectric effect also previously. So this photoelectric effect proved, we say, particle nature of light. Particle nature of light. Okay. So this was the strong proof for the wave nature of light, and this was the strong proof for the particle nature of light. But my dear friends, if you remember, previously I have told you, in modern physics, we used to consider the light as a photons. Light is made up of small particles, photons. But here, we say in wave optics, I'll just write over here, in wave optics, I'll just say, we consider light as a wave. We consider light as a wave because we'll have to prove the Young's double slit experiment over here. That is only possible if you consider the light as a wave. So from now onwards, if I say you have got a light source over here, if I say you have got a light source over here, so we say these are the waves coming out of the light source. So from now onwards, we'll be saying that this light is made up of waves, or this light is a wave itself in this chapter. We know it has dual nature, but here we'll be considering this as a wave. Now, the first topic, that's the reason we call it the wave optics. Optics is the study of light. Wave means wave nature. Here we study the wave nature of light. Now guys, the first topic of the chapter is Huygens Principle. The first topic of the chapter is Huygens Principle. I would want you guys to give me the 100% attention over here. Everyone means everyone. Look at the board. Now see. Let's suppose guys, you are taking a tank over here in which water is filled. This is the water inside the tank. Okay. Now this is a tap over here. Now if I say water droplet is falling into this tank. Okay. We say water droplet is falling into this, into this tank. What happens? We say when this drop falls, we say some kind of waves are being produced over here. Okay. So this is a kind of wave, or you say a disturbance. This is a kind of, we say, wave or a disturbance. Either you say it a wave or you say it a disturbance. Okay. And can I call this as a source of disturbance? This will be source of disturbance. Why? Because this is disturbing the water over here. Now this is the side view. This is the side view. Let's take a look at the top view. You are seeing this from the top. If you try to look at the top, it will look something like this. This is the particle, source particle. Then these are, we say, the waves. It looks something like this. This is the disturbance wave created, something like this. It's like you are taking a stone and you're throwing it into the water. Okay. And then those ripples will be created over there. And that's what we call the waves. We say simply, these are the waves, disturbances over here. Now guys, this is the example of water. I took this because this gives the more feel, because you would have experienced this in your real life. That's why. Now let's suppose if I take a light source over here. If I'm taking a light source over here. Okay. We say same is in case of light source. Let's suppose you are taking a bulb over here. When it comes to the bulb, we say around this bulb, similarly, when the light comes out of the light source, it comes something like this only. This is the example of water, but when you take a light source, proper light source, we say light goes also like this only. Okay, so we say this is a light source. We say light comes out of this, so it is creating something like this. It is creating these wave fronts, we say. Exactly. We say same is in case of a light source, bulb, which acts as a source of disturbance. Like here, this acts as a source of disturbance. In case of when you take a light source bulb, we say that acts as a source of disturbance. Okay, when the light comes out of the bulb, it basically goes around something like this only. Okay, now my dear friends, I'll show you that over here in this one. Let's suppose you are taking a bulb over here. We say light comes out of the bulb. Okay, now this is the source particle. This is the bulb which gives the light. Okay, this is the source particle over here. Now my dear friends, you take a look in this particular case. When the source particle falls over here onto the into this water, what happens? It creates the disturbance. Means this is the source particle, primary particle. So basically the particles which are the neighboring particles to this particular source particle, it transfers the energy to these particles. Guys, understand this very carefully. This source particle, there are so many other particles present over here. So we say this is the particle, this is the neighboring particle, neighboring particle, neighboring particle, neighboring particle. So when this falls into the water, it transfers the energy to these particles. Now these particles will oscillate. They come up, they go up, okay, and then falls back. Now they start vibrating. When they vibrate, we say wave is created. Similarly, these source particles further disturb their neighboring particles. They transfer the energy to their neighboring particles. Similarly, the wave is produced like I am showing you over here. This is the source particle. It is disturbing its neighboring particles. Like it is mentioned over here. We say the source particle disturbs the neighboring particles. The source particle disturbs the neighboring particles. And when they are joined with a common tangent, if you say this is the source particle, it is disturbing its neighboring particle, neighboring particle, neighboring particle, neighboring particle. Disturbing means it is transferring the energy. Initially, that neighboring particle was at rest. When that particle gains the energy, it comes up. It starts oscillating. It goes up in the air. Okay. And my dear friends, if you join these with a common tangent, this is what we call, this forms the wave front. This is what we call the wave front. Okay, like over here, if you join these particles with a common tangent, common line over here, this becomes the wave front. So what are these? From now onwards, if somebody asks you, sir, what are these? These are what we call the wave fronts. These are what we call the wave fronts. Okay. So join these with a common tangent and we say this forms the wave front. Now, my dear friends, this particle, this is the source particle, this primary particle or source particle. The neighboring particles which forms the wave front, these are called the secondary wavelets. These are called the secondary wavelets. Okay, it's mentioned over here. Now, similarly, this neighboring particle disturbs its neighboring particle. This is the neighboring particle. Okay. And there would be one more somewhere around over here, Similarly, this neighboring particle is also disturbing its neighboring particles. This neighboring particle, this particle is also disturbing its neighboring particles. Now, join these neighboring particles with a common tangent. Join these neighboring particles with a common tangent. So we call this as the secondary wave front. Okay, these secondary wavelets will further disturb their neighboring particles and produce the waves. And this will be another wave front that we have exactly over here. Like my dear friends, if we see it over here, these neighboring particles are now disturbing their neighboring particles. Okay, something like this, something like this, something like this, something like this, something like this. Okay, okay. Now I'll mark those particles over here. These particles, these particles, these particles, these particles. Now join these with a common tangent. This is what we call the secondary wave front. Okay, so we have the primary source particle, and it falls, and when it falls in the water, okay, it disturbs its neighboring particles, creating the wave front. Then those neighboring particles will disturb their neighboring particles, creating another wavefront, and this happens, this transfer of energy happens, and we say disturbance is carried further, and this is what we call the production of the wave. And I am giving you the example over here, example of the water, but the same thing happens when you take a light source. Okay, you have got the primary source. I've got the primary source. It is disturbing the neighboring particles. Okay, the neighboring particles disturb their neighboring particles, and the wave is produced, and the transfer of energy happens. I would want you guys to tell me how many of you understood this. This is Huygens principle. This is Huygens principle. Okay, I would want you, this was the concept of wave fronts, or we say Huygens principle. I would want you guys to tell me how many of you understood this, and with the thumbs ups and fire emojis in the chats, with the fire emojis in the chats only. Tell me, guys, how many of you understood this properly? Now, guys, so you got the concept of the wave fronts, I hope. Let's move on to wave fronts of different sources. Let's suppose you have got a point source, like you have a bulb over here, that's like a ball. Okay, you have a bulb over here, that's like a ball. So basically, in case of a point source, we say wave fronts are like this is a point source. Don't you think that wave fronts will be spherical? Yes. So spherical wavefront, spherical wavefront. Okay. So wave fronts will be spherical. So if you have a point source creates the spherical wavefronts. Okay. And my dear friends, so we say these are the spherical wavefronts. These are the spherical wavefronts over here. And this is the direction of the energy flow. Okay, energy flows away from this. Okay, like you have a bulb over here, so wave fronts will be spherical goes away. Okay, next, guys, let's suppose you have got a linear source over here. Example is tube light. So if you have a tube light, so we say in case of the tube light, it is creating the cylindrical wave fronts. Tube light creates the cylindrical wave fronts. Okay, tube light creates the cylindrical wave fronts. Okay, this is the cylindrical wave front over here. Or we say this is the linear source. You can also call it the linear source over here. Okay, now my dear friends, let's suppose you have got the parallel rays. Okay, these are the parallel rays. Okay, like light source is at a very far distance. The rays are coming as parallel light rays over here. So in this particular case, whenever you have the parallel rays, how you are supposed to make the wave fronts over here? You will make the planar wave fronts. Always remember, here wave fronts are planar. If you have the parallel rays, we say wave fronts will be planar. Just make a plane sheet, something like this. These are the planar wave fronts. Okay. Yes. And like if you have converging rays, guys, in this particular case, the wave, these are the rays which converge at a point. If the rays are converging, light, sir, what is a ray? If you say light is coming out of the light source, means you can consider it's a ray coming out of the light source. Okay. And sir, how are we supposed to draw the wavefronts over here? You are supposed to draw the wavefront such that it should make 90 degree with the, we say wavefronts, with the rays. So this should make 90 degree. Here it is 90 degrees, 90 degrees, 90 degrees. At every point it should make the 90 degrees. Okay. And if you have the diverging rays, means light rays are diverged something like this. Light rays are diverged something like this. Just remember over here, whatever I say, keep that thing in your mind. And here you are supposed to make the wavefronts in such a way such that here also it should make 90 degrees. Here also it should make 90 degrees. Okay. So in case of diverging, it is something like this. Now guys, reflection by a plane mirror. Guys. If you remember previously, ray optics, I said this is a reflecting surface, plane mirror. Okay. I said over there, this is a plane mirror. Okay. And on this plane mirror, I said light is falling, light is incident, and it is reflected something like this. So this was the incident ray, this was the reflected ray, and this we were considering as normal. But right now, in the chapter wave optics, we are considering light as a wave. Yes, sir, 100% agreed. If you consider the light as a wave over here, and we know wave itself is made up of wavefronts. Yes, sir. So, if light is following the law of reflection in ray optics, why cannot the same light obey or follow the law of reflection while basically taking the wavefronts instead of the ray? So here, if you have to define, guys, we say law of reflection can be proved using wavefronts also, considering light as a wave also. See guys, we say this is a mirror over here. We say this is light falling something like this. And when it comes to the light, we show light with the help of the wavefronts. So we say this is light falling. So these are the wavefronts falling. You can understand it something like this. Like if I'm saying I have got over here, if I'm saying I have got over here, this is a reflecting surface. Okay. And we say incident light is falling over here. You can say, sir, these are the wavefronts falling over here. These are the wavefronts falling over here. These are the wavefronts falling. And when wavefronts falling, light falling, wavefronts falling, we say it is reflected. So we say these are the, now you can say in this particular case, these are the incident wavefronts. These are the reflected wavefronts. This is the incident light. This is the reflected light. And this is the reflecting surface. That's what I'm trying to say over here. That's what I'm trying to say over here. We say incident wavefronts are falling on this mirror. And these are reflected over here. These are reflected over here. Yes. Okay. So this is the law of reflection. Okay. While considering the light as a wave. Okay. And this is the normal over here. This is the normal over here. Angle of incidence, angle of reflection. Simple thing. Simple. Sir, is it possible over here also? A reflection from the curved mirror. A reflection from the curved mirror. If you have got a concave mirror over here, guys, this is the concave mirror. This is polished from the outer side. If you have watched my ray optics lecture, then this should be clear to each and every single student out there. Okay. Now, guys, these are the light rays falling over here. We say after reflection, these are the incident light rays, planar. Okay. And these are the reflected wavefronts, Guys, here, incident wavefronts are planar. Reflected wavefronts are planar. This is in case of a plane mirror. But when you take the curved mirror, we say in case of the curved mirror, when these incident wavefronts fall, We say after reflection, we saw that the wavefronts are we say over here, something like this. Okay, something like this, kind of spherical. Okay. Similarly, guys, we say if you have a convex mirror, if you take a convex mirror, so incident wavefronts, guys, here, these are the incident wavefronts. And here incident wavefronts are planar. Means this is a light source over here. From the light source, wavefronts are leaving. When it falls onto this convex mirror, we said these will be reflected and the light rays will be reflected something like this. In case of this is called the converging mirror also. So when the light rays falls onto the converging mirror, they will be after reflection, they will be converged. Okay. Now draw the incident wavefronts. Like I'll show you over here. Guys, let me give you the proper feel. So that no confusion is left. If I'm saying in this particular case, this is a concave mirror. Okay. We say light is incident on this concave mirror. These are the light rays, parallel light rays. Since this is a converging mirror, after reflection, it will converge the light rays. Okay. After reflection, it will converge the light rays. Now, my dear friends, can I say incident light rays are over here planar? Okay. Why? This is called the incident light ray, incident ray. Okay. This is called the incident wavefront. Incident wavefront. Sir, why should you make the incident wavefront as planar over here? This is ray, incident ray. This is incident wavefront. Okay. Because it should always make 90 degree. And this is the reflected ray. This is the reflected ray. And if you have to make the what do we call this as a wavefront over here? So we say wavefront would be something like this, because wavefront should make 90 degree with the light rays. So these are what we call the reflected wavefronts. Okay. So incident wavefronts are planar, reflected wavefronts are spherical over here. I hope this is clear now. And when it comes to the reflection on the plane mirror, incident wavefronts are planar, reflected wavefronts are also planar. As simple as that. Here, incident wavefronts are planar, reflected wavefronts are spherical. Now, if you have this convex mirror, convex is a diverging. Now, guys, let me show you over here. I'll make the convex mirror something like this. This is the convex mirror. It is polished from the inner side, and this is polished from the outer side. Now, don't ask me, sir, what is this polish and all? Guys, see, we say, let's suppose these are the incident rays. These are the incident rays. And after reflection, we said these will diverge. These will diverge. Okay. So incident ray, and you call this as reflected ray. Incident ray, reflected ray. Now tell me one thing. In this particular case, can I say, sir, incident wavefronts will be planar? Why? Because light rays are parallel, so incident wavefronts will be planar. And what about the reflected wavefronts? Those will be spherical. So we say these are reflected wavefronts, and these are incident wavefronts, planar, and these were spherical. And same thing is mentioned in this diagram. Is this crystalline clear? Please give me the signal in the chats, ladies and gentlemen. So law of reflection can be proved here also if you consider the light as a wave. That's what I'm trying to say. Okay. Next. Sir, can we prove the law of refraction also if we consider light as a wave? Yes. What does law of refraction say? Guys. What does the law of refraction say? if you have got a surface over here, above the surface you have got medium 1, below the surface you have got medium 2. There are two different medias over here. Okay, this is medium 1 and this is medium 2. If I'm saying light is entering from one medium to another medium, okay, if I say it is entering from rarer medium to denser medium, we say it is bent towards the normal. It is bent towards the normal. So, falling of light, entering or we say transferring of light from one medium to another medium is what we call the refraction. Now, guys, we have proved this when we consider the light as a ray. Let's consider light as a wave. Guys, above the surface, this is the medium 1. Okay, above the surface, you have got the medium 1. Okay, air, it may be something else. Below the surface, there is another medium. Let's suppose it is water. Above the surface, air, below the surface, water. Now we say light is falling. If light is falling, you show it here with the help of the wave fronts. Wave fronts are planar. So we say this light basically enters another medium. We say it is bent towards the normal. Okay. And when it is bent towards the normal, these are the refracted wave fronts. Incident wave fronts, refracted wave fronts. Okay. Now you can understand it something like this also. This is a surface and these are, we say, wave fronts falling over here. These are the wave fronts falling over here. This is the medium 1 and this is the light going something like this. So I can say over here, bending of light is taking place. So you can say this is the refraction over here. When light enters from one medium to another medium, that's what we call the refraction. Okay. Refraction through prism. Like if you remember, previously in wave optics, you said, sir, light is entering the prism. This is the incident ray. So this prism has got a refractive index. So it is another medium. Light is entering from air to medium. It is bent something like this. Then again it leaves the medium. It is again bent. So this is what we call the refraction through prism. Similarly, if you do the refraction through prism over here, you take the prism in this particular case and we say these are the incident wave fronts entering. Okay. Now, if this is the incident ray, we say it is bent. Now make the incident wave fronts. Now these are the refracted wave fronts. Again, when the light leaves the prism, again the light is bent. Okay. Now here you make these refracted wave fronts. Incident wave fronts, refracted wave fronts. So even if you consider the light as a wave, refraction through prism is also possible. If you consider light as a wave, refraction here is also possible. I hope this is crystal clear to each and every single student. I hope this is crystal and clear to each and every single student. Guys, give me the signal in the chats, ladies and gentlemen. If you have not liked the session yet, I would want you guys to smash the like button as soon as possible. Okay. Tell me, guys, is this crystal clear to each and every single student? Great. Now, guys, let's discuss the wave equation a bit. Guys, let's suppose we have got a wave on a string. Like I'll take a rope and I'll connect it with the wall and then I'll start producing the waves over here. Okay, that's a wave on a string. What happens in this particular case is, so when I displace, this is the source of disturbance over here. When I disturb this with the source particle, so it is transferring this primary particle over here. This is transferring the energy to the next particle. Now it starts vibrating. Okay, it starts vibrating. And then it transfers the energy to the next particle, then that starts vibrating. Now it gives the energy to the next particle, then it starts vibrating and this wave is basically produced. Then we write this equation of wave as y is equal to a sine of omega t plus minus phi. A is the amplitude. What is the amplitude of the wave? How high the particle can go over here? This is called the amplitude. This is called the amplitude. Okay. Okay. Omega angular frequency, T is time, and phi is called the initial phase. Okay. Simply, I would want you guys to remember this as of now. Direct. This is the equation of wave. This is how we write the wave equation. This is how we write the wave equation. Okay. Now, guys, what I need in this particular case is, this is the amplitude. Amplitude means how high the particle can go. Maximum. Now, if I say, my dear friends, over here, just take a look. First, I need to make you understand the path difference. Okay. Then I'll make you understand the phase difference. Path difference and phase difference. Okay. Now, my dear friends, let's suppose, if I'm saying in this particular case, there is a wave which is traveling from A point to B point. This is the wave which is traveling from A point to B point. And it has traveled how much? 5 kilometers over here. A point to this M point. There is another wave. Guys. There is another wave which is traveling from B point to M point. This wave is traveling, we say 10 kilometers of distance. If I ask you how much is the path difference, this has traveled this much path, this has traveled this much path. How much is the path difference in this particular case? We say path difference delta x is, we say how much this has traveled, that is 10, minus how much this has traveled, that is 5. 10 minus 5, and that is 5. So what is the path difference in this particular case? That is 10 minus 5 is 5. 10 minus 5 is 5. This is the path difference. Okay. Yes. Because this has traveled 5, this has traveled 10. Simple. How much second wave has traveled more as compared to the first? Then we say phase difference. Guys, understand one thing very carefully. How do we explain the phase difference? Let's suppose you have got two waves, this yellow wave and this blue wave. Okay. Now both the waves are starting from 0 over here. Let's suppose this is t. So at time t is equal to 0, we say yellow wave is at minimum. Its value is minimum. And this blue wave has also minimum value. We say after some time, let's suppose at time t is equal to t by 4, we say this yellow becomes maximum. Even blue also becomes maximum at the same time. Then we say when blue becomes minimum, at that time also we say yellow becomes minimum. Okay, just a second, guys. Okay. Now guys, we say here the two waves have the 0 phase difference. Here the two waves have the 0 phase difference. Why? Because when this wave yellow is at minimum, blue is at minimum. When this is at maximum, this is at maximum. So they have got the phase difference of 0. We say they have got the phase difference of, in this particular case, 0. Okay. Yes. Now guys, let me give you one more example in this particular case. See, you have got this blue wave, you have got this yellow wave. When blue wave is at minimum 0, yellow wave is at maximum. Then when blue goes maximum, yellow goes minimum. When blue goes minimum, yellow goes maximum from the lower side. In this particular case, I can simply say phase difference is pi by 2. When one is minimum, other is maximum. When other is maximum, another is minimum. So here phase difference between these two waves is maximum, is pi by 2. Let's suppose I'll take these two waves over here. This is yellow wave. this is blue wave, this is blue wave. In this particular case, both starts from 0, but when this goes maximum from the upper side, this goes maximum from the lower side. Plus A minus A. In this particular case, we say phase difference is 180 degrees. 180 degrees. Okay. Here phase difference phi is, or delta phi is pi by 2. Here phase difference is 180 degrees. Okay. Guys, tell me, is this crystal and clear? How many of you understood this? Is this crystal and clear? All the people out there, let me know in the chats. Now guys, look, now guys, take a look. You have got over here. Yes, great. Now guys, take a look. Let's talk about constructive and destructive interference. Okay. So first we need to understand what is constructive interference. Guys, see. Let's suppose if I make the wave over here. This part of the wave is what we call the crust, and this part of the wave is what we call the trough. Okay. Crust, trough. Now guys, let's suppose there is one wave which is coming from this side. Okay. This is the amplitude of the wave. Okay. A is the amplitude of the wave. I told you this is the amplitude of the wave. So the wave is coming from this side, amplitude is A. And there is another wave which is coming from this side, the amplitude is A. So this wave is coming something like this, another wave is coming something like this. Okay. So here. When this wave becomes maximum, this is also maximum, peak. When this wave is minimum, this is also minimum. In this particular case, when the two waves meet, maximum, A. So we say the resultant wave will be bigger. Two waves are meeting, resultant wave will become bigger. And amplitude here is 2A. And in this particular case, we say phase difference is 0. When phase difference between the two waves is 0, then only we say when one wave is at maximum, another is also at maximum. When these two waves meet, or when crust of the two waves meet, amplitude becomes large, amplitude becomes 2A. It is called constructive interference. In simple words, what is constructive interference? Meeting of crusts, or when two waves meet which have got the same, which are in phase, okay, which has the 0 phase difference. So we say they have 0 phase difference. So net amplitude is A plus A, that is 2A. Now guys, example is over here. You have got this wave, you have got this wave. Okay. And what will be the resultant wave? In this particular case, the resultant wave will be this, with the bigger amplitude. Because when this is at minimum, this is at minimum. This is at maximum, this is at maximum. So here phase difference is 0. We say in this case, resultant amplitude will increase and constructive interference will take place. Next. We say when crust and trough of the two waves meet, the amplitude becomes 0 and it is called destructive interference. Like there is one wave coming from this side when this is maximum, another wave coming from this side, this is minimum. Crust and trough are meeting. This is crust, this is trough. So in this particular case, this is the resultant wave. And what is the amplitude of this? 0. So we say here destructive interference takes place. Your destructive interference takes place. Okay, yes, yes. Like example over here, we have got the two waves. This is the first wave over here starting from minimum. And this is another wave. If this is going up, this is going down. When this is at plus A, this is at minus A. We say in this particular case, guys, crust and trough are meeting. Here, trough of this, crust of this. Crust of this, trough of this. In this particular case, we have already seen phase differences 180 degrees. So when phase difference is 180 degrees, we say destructive interference takes place, and net amplitude in this particular case is 0. Okay, so this was the real life feel of constructive and destructive interference. Now guys, sir, we got the real life feel of constructive and destructive interference. Please give us the proof of constructive and destructive interference with the mathematical equations, using the mathematics. Let me show you guys. Let's suppose you have got the two waves. This is the equation of the first wave, like this is the wave over here. This is the equation of the second wave. This is the wave over here. A1 sine of omega t, A2 sine of omega t plus phi. Phi is called the phase, initial phase. Here initial phase is 0. Here it is phi. Okay. Now guys, what I want you guys to do is, we say in this particular case, A1 is the amplitude of first wave, how high the particle can go. A2 is the amplitude of the second wave. In this case, what I'm trying to say is that we say represent the amplitude with a vector. I would want you guys to represent this amplitude with a vector. See guys, if I am saying you have got y is equal to A1 sine of omega t plus 0. Another wave is y2 is equal to A2 sine of omega t plus pi by 4, or we say 30 degrees. What is difference between this wave and this wave? Sir, till here it is exactly similar, but here it is plus 30, here it is nothing. So means they have got a phased difference of phi is how much? 30 degrees. So what I'm trying to say in this particular case, if I show you the A1 over here amplitude something like this. If I say A2 will be something like this, this is A2. Sir, why did you make A2 over here? Because they have got the phase difference of phi. Angle between these two is phi. This is the meaning of phi. Okay? Phase difference. If I say phi is pi by 2, means in that particular case, the phase difference between the two waves is pi by 2, like over here. These two waves have got how much phase difference? Pi by 2. They have got 180 degree. Pi by 2 means 90. Okay. Now guys, if you have the two vectors, can you find the resultant vector? So you find the net amplitude of these two waves, A1, A2, this will be, sir, A net. And if you remember, there is a simple technique by which we find the resultant of the two vectors. What is that? We say A net square is equal to, okay? How to find the resultant of two vectors? A net square, resultant square is equal to, we say A1 square plus A2 square plus, we say 2 times of A1, A2, twice A1, A2, then we say cos of pi. Pi is the angle between the two vectors. Okay, this is how we find the resultant in this particular case. Now guys, tell me one thing. When it comes to the constructive interference, I recently told you what should be the value of phi. Phi should be 0. So we say in case of constructive interference, we say phi should be equal to 0 degree. Okay. If phi is 0, what is the value of cos phi? Cos phi will be 1. Cos 0 is 1. So in that case, we say a net square will come out to be, that is simply, I'll write over here a1 square plus we say a2 square plus we say twice a1 and then we say a2. Cos 0 is 1. Now it is a square plus b square plus 2ab. So you can write over here a net square in this particular case will be, that is a1 plus a2, a plus b whole square. You can write it something like this. Yes. Now let's suppose if I say amplitude of the first wave, if a1 is equal to a2 is equal to a. If amplitude of the first wave is equal to the amplitude of the second wave is equal to the amplitude of the third wave, sorry, is equal to a. So can you then say, sir, a net square will be, that is a1 plus a2, that is a plus a, that will be 2a whole square. Okay. a1 plus a2, that will be 2a in this particular case, because a plus a is, we say 2a. And then tell me guys, this a net square will be, guys, this is 2a, it becomes 4a square. Now take the square over here. This a net in that case will be, that is root, take the square over, it becomes root 4 is 2 and this is a. So net amplitude in that particular case is 2a. Now you guys see, I said the same thing directly over here. Net amplitude is 2a. When crust and crust meets, when constructive interference takes place, when phi is 0, whatever you want to say, everything is same. Okay. Is this clear? Guys, give me the signal in the chats. Great. Now. Guys, let's talk about the destructive interference. Can I say in case of destructive interference, in case of destructive interference, okay, in case of destructive interference, guys, can we say when it comes to the destructive interference, what is the value of phi? That is 180 degrees, or we say pi. Pi means 180 degree. Because recently I told you, phi, when phi is 180 degrees, see over here. Okay, where is it? Yeah, here. In case of destructive interference, phi is 180 and resultant amplitude is 0. Now see, how do we find the resultant amplitude? We say a net square is equal to a1 square plus a2 square plus 2 times of a1, a2, we say cos of pi, cos pi. Cos pi in this particular case is -1. Cos 180 is -1. So this will come out to be a net square is equal to a1 square plus a2 square minus 2 times of a1, we say a2. Okay. Now guys, it is a square plus b square minus 2ab. So can I write it something like this? This will be a minus b whole square, a1 minus a2, and then we say whole square. This is the net amplitude in case of destructive interference. Okay. Now. can I say in this particular case, if A1 is equal to A2 is equal to A, if amplitude of first wave is equal to amplitude of second is equal to A, so I can say in that particular case, A net square will come out to be A1 minus A2, that is A minus A. So A minus A whole square, this will be 0. So net amplitude in that particular case will come out to be 0. Is that clear, ladies and gentlemen? So that's what I was saying previously. Okay. Yes. Net amplitude in that case is 0. So this is in case of destructive interference. Let's talk about the intensity. Guys, in the modern physics also we have discussed the intensity previously. In the modern physics also we have discussed the intensity. So when it comes to the intensity, we say intensity is simply power upon area, or we say energy per second per unit area. Guys, over there, I told you intensity is simply, let me just give that example over here very quickly. You have got the two light sources. Okay. So we say light is coming out of this light source over here and it is falling on this surface. Okay. Light is coming out of this light source that is falling on this surface. Okay. If light is coming and falling on this surface, we say this is energy falling. And on this area. Now, how much amount of energy is falling on the unit area every second? That is what we call the intensity. I say, sir, this is a good bulb. Every second, lot of means this is a good bulb. Means it has got a it is 100 watt power. It has got 100 watt power. It will give you more energy. If it gives you more energy every second, and if I place my hand over here, on my hand every second more energy is falling. So I say intensity is large. If brightness is large, intensity is large. Energy is large, intensity is large. As simple as that. Okay. So how do we define intensity? It is power divided by area. What is power? Power is energy upon time. And then you have area over here. Okay. Now guys, I just want to directly remember over here. Remember. R-E-M-B-R. Remember. R-E-M-E-M-B-E-R. Remember. We say intensity is proportional to amplitude square. Directly, when it comes to the intensity, always remember, sir, if amplitude is large, we say intensity is large. If intensity is large, we say amplitude is large. So intensity is proportional to the amplitude square. Now guys, what I want you to understand over here is something else. See, we say as can I say A net square is equal to A1 square plus we say A2 square plus 2 times of A1, A2 we say cos of phi. This is intensity. This is the net amplitude. What I'm telling you is that you replace this amplitude square with the intensity, because intensity is proportional to the amplitude. Amplitude is large, intensity is large. Intensity is what? How much amount of energy is given by the bulb every second unit on unit area. So we say here replace A square with I. I want you guys to replace A square with I. Okay. So if you replace this A square with I, can I say A net square? This will be over here simply I net is equal to A1 square. This will be simply I1 plus A2 square. This will be simply I2 plus 2 times of, guys, this is A. If you are saying intensity is proportional to A square, what will be the value of A? Take the square over here. A will be equal to root I. Yes. So instead of this A1, I'll write over here root I1. Instead of A2 over here, I'll write over here root I2. And then I say cos of phi. This will be the formula for the intensity. This will be the formula for the intensity. Okay? This will be the formula for the intensity. And this is the formula for the amplitude. This is the formula for the intensity. Intensity. Okay. Now tell me guys, when it comes, I have already calculated the amplitude in case of the constructive interference, that is 2A. I have already calculated the amplitude, net amplitude in case of destructive interference, that is 0. Let's talk about intensity. Guys, see. We say now for constructive interference, let's find net intensity. Like you have got the two waves, light waves. Okay. They are constructively interfering. We have to check how much is the net intensity. See guys, we say for constructive interference, what is the value of phi? That is 0. So what is the value of cos phi? That will be 1. Yes, cos phi is 1. Now tell me one thing. Can I say when it comes to the net intensity, you say, sir, that will be I1, I2. Okay, I1 plus I2. You say I1. Then we say plus I2 plus 2 times of I1 under root of I2 cos of phi. Cos of phi. Okay. Okay. Now, when it comes to the I net is equal. Guys. So what is the value of cos phi over here? We say cos phi over here will be cos 0. Cos 0 because phi is 0. So it will be 1. So it will be I1 plus we say I2 plus 2 times of root I1 or root I2 because cos 0 is 1. Okay. We can say it something like this over here. This will be the resultant intensity. This will be the resultant intensity. Okay. Now, my dear friends, let's suppose if I ask you in this particular case, what if I1 or can you write it like this, guys? I would want you guys to write it like this. I net is equal to, we say under root of I1 plus under root of I2 whole square. Sir, how can we write it? See. This is A plus B whole square. Open it. You'll say A square. So it will be a root I1 whole square plus B square. That will be root I2 whole square plus 2AB, 2 root I1 root I2. Now this square root cancels, this square root cancels. So it becomes I1 plus I2 plus 2 times I1. Yes. So we can write this something like this. So this is what we call the maximum intensity. Sir, why do you call it the maximum intensity? Because in case of constructive interference, we say amplitude becomes maximum. If amplitude is maximum, we say intensity will be maximum because intensity is proportional to the amplitude square. Now, what if somebody says if I1 is equal to I2 is equal to, we say I naught. So can I say in that particular case, I net will be, so this is under root of, we say I naught plus we say under root of I naught whole square. If both the intensities are same, if the intensity of the two waves are same, so this will become 2 times of I naught whole square, 2 times under root of I naught whole square. So this will be 2 square is 4 and this will be over here I naught. So this is what we call the net intensity in that particular case. But this is what we call the maximum intensity also. Okay. So keep this in the box. Keep this in the box because this is the formula that we actually got. Keep this in the box also. Now guys, let's talk about the destructive interference. Now for destructive interference, let's find net intensity. Let's find net intensity. Okay. Guys, when it comes to the destructive interference, what is the value of pi? That is pi, 180 degrees. So could you please tell me what will be the net intensity? That is I1 plus we say I2, then we say plus 2 times of root I1, root I2, then we say cos of pi. Cos 180 is minus 1. So it will be net intensity in that particular case will be I1 plus we say I2. Cos 180 is minus 1. Take that minus over here. 2 minus 2 times of I1 under root of I2. So we can write this something like this. I net will be, that is under root of I1 minus under root of I2 whole square. Because if you open this up, it will become this only. If you open this up, it will become this only. Now guys, in this particular case, what I want you to focus is, and this is what we call the minimum intensity. Because when destructive interference takes place, amplitude is minimum, 0. If amplitude is minimum, intensity will be minimum because intensity is proportional to the amplitude square. Now, if I1 is equal to I2 is equal to I0, let's suppose. So I can say I net will be, that is root I1. So under root of I0, okay, then minus we say under root of I0 whole square. So root I0, so net intensity in that case will be 0. In this case, net intensity will be 0. This is the minimum intensity that we have got. And directly, if somebody asks you what is the ratio of maximum and minimum, this is the maximum intensity under root of I1 plus root I2 whole square divided by minimum is under root of I1 minus root I2 whole square. Is that clear, boys and girls? Give me the signal in the chats, ladies and gentlemen, if everything is crystal clear to each and every single student. Tell me, guys. Great, 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 great. Now, let's take a look at the question. If two waves represented by y is equal to, first wave over here is given as y1 is equal to 4 sine of omega t. Y2 in this case is given as, that is 3 sine of omega t plus pi by 3. Could you please tell me what is the phase difference between the two? Sir, it is pi by 3. So phi over here is pi by 3. You guys are supposed to tell me what is the amplitude A1? A1 is 4 because this is A1 sine omega t, A2, and A2 in this case is 3. You guys are supposed to tell me what is the resulting amplitude. When it comes to the net amplitude, A net square, it will be simply, that is A1 square plus A2 square plus 2 times of A1, A2 cos of phi. And what is the value of, okay, just put the values. It will be 4 square plus 3 square plus 2 into 4 into 3 and cos of pi by 3. Cos pi by 3 is cos 60 degrees. That is 1 by 2. Okay. Okay. Tell me what is the answer, guys? Simple calculations you guys are supposed to do. Okay. So this will be A net square. So if you take A net over here, this will be under root of this one over here. Okay. And if you solve it, it will come out to be approximately 6. This is A net. Approximately 6. root 37, so approximately 6. Okay. Next, two beams of light having intensities I1 and I2. Guys, take a look over here. You have got two beams of light having intensities I1 and I2. Means there is one light beam, its intensity is I. And another light is, its intensity is, we say 4I. I and 4I. Its intensity is I and 4I. To produce a fringe pattern on the screen, the phase difference between the two, so phase difference over here is given as, the phase difference over here is given as pi by 2. Phase difference is pi by 2. At point A, guys, the phase difference is pi is equal to pi by 2 at point A. So basically it is like these two waves are meeting at point A. These two waves are meeting at point A. So phase difference is coming out to be how much? Pi by 2. In this case, when they meet at point A, phase difference is pi by 2. And then it says 2 pi at point B. When the same two waves over here, we say, sir, this is the point B. When meeting at point B, pi is equal to pi at point B. At point B, phase difference is, okay, 2 pi. It is 2 pi. Pi is given as 2 pi. Then find out the difference between the resultant intensities. Guys, see. Find out the difference between the resultant intensities. I would want you to focus exactly over here. First, you find let's find the resultant intensity at point A. Let's first find the resultant intensity at point A, at this point A. How will you find? Sir, I'll just write, this will be I resultant at point A is equal to I1 plus I2 plus 2 times of root I1, root I2, then we say cos of phi. This is the general formula that we use. Okay, this is the general formula that we use. And can I say in this particular case, this IA will come out to be I1. What is the value of I1? That is I. And then we say 4I plus, we say 2 times of root I1. Okay, instead of root I1, 2 times of root I under root of 4I and cos of phi. We say cos of pi by 2. Cos pi by 2 is how much? 0. So this term will become 0. 4I plus I is 5I. So IA will come out to be 5I. So resultant intensity of these two, this I and this is 4I. It is 5I at this point. Okay. Now, let's find resultant intensity at point B. Let's find resultant intensity at point B. So how do we find the resultant intensity at point B? IB is equal to I1 plus I2, that is I plus 4I, then plus 2 times of root I or root 4I. At point B, what is the value of phase difference? Cos 2 pi. That is cos 360. Solve this. IB will come out to be 9I. Now guys, IA is 5I. IB is 9I. Could you please tell me what is the difference? We say difference. So difference will be simply IA, or we say IB minus IA. Difference in their resultant intensities. So that will be 9I minus 5I is equal to 4I. 4I is the difference. Is this clear? Now, let's move on to the next question. Two coherent sources, each emitting light of intensity I naught, interfere in a medium at point where the phase difference is 2 pi by 3. Then the resultant intensity will be. Guys, simple. It is a simple question. In this case, you have got 2-point sources in which intensity I1 is given as I naught. Another source also has intensity I naught. Phase difference is given as 2 pi by 3. You are supposed to find the resultant intensity. And when it comes to the resultant intensity, it is simply I1 plus I2 plus 2 times of root I1 root I2 cos of 2 pi divided by 3. Just put the values and get the answer. That's it. Next, consider 2-point waves. Consider interference between waves from two sources of intensities I and 4i. Find the intensity at the point where phase difference is pi. Once again, the same question. In this particular case, I1 is given as I and I2 is given as 4i. I2 is given as 4i. Okay. And phi in this case is given as pi. You guys are supposed to find out what is I net. This is your homework and answer should be 1. Next. Yeah. Take a look over here. The ratio of intensities of two waves is 25:1. Guys, see. You have got the two waves. Their ratio of intensity is I1 divided by I2 is 25:1. The ratio of intensity of two waves is 25:1. 25/1. They are producing the interference pattern. They are producing the interference pattern. They are producing the interference pattern. The ratio of maximum and minimum intensities will be, guys, see. We said this is the ratio of the two, means you have got the two waves. This is the first wave, this is the second wave. Intensity of the first wave is, ratio is given as I1 is to I2 as 25:1. You have to find the ratio of the maximum intensities. Guys, when it comes to the maximum intensity, if you remember, I told you that is under root of I1 plus under root of I2 whole square divided by if I say intensity minimum, it is under root of, we say I1 minus under root of I2 whole square, already discussed. Yes. This is how we find the maximum intensity, minimum intensity if I1 and I2 are given. So in this case, can I say what is the value of I1 by I2? 25:1. So it will be a root 25 plus root 1 divided by here a root 25 minus root 1 and you have got whole square. So what will you write? Root 25 is 5 plus 1. Root 25 is 5 minus 1. Okay, this is whole square. This is 6/4. And this is 2s are, this is 3s are. So ratio will be 3/2. So the ratio of maximum and minimum intensities will be 3:2. Two intensities, the intensity ratio of two waves is 9:1. Means I1 divided by I2 is given as 9:1. They produce the interference. These waves produce interference. The ratio of maximum and minimum intensity is once again the same question. I max divided by I minimum. What will you say? Sir, under root of I1 plus under root of I2 whole square divided by under root of I1 minus under root of I2 whole square. Can I say in this particular case, this is a root I1. A root I1 is how much? As it is 9:1. So it will be a root of 9 plus 1 divided by a root of 9 minus 1 whole square. So this is 3 plus 1, that is 4 divided by 3 minus 1, that is 2 whole square. This is 2 So it is 4:1. Okay. Because 2 ones, 2 twos, 4. 2 square is 4. 4:1. Option D. Okay. Once again, the question on the same. Two sources with the intensities I0 and 4I0 respectively interfere at a point in the medium. Then the maximum and minimum intensity is possible to be. Here you have to find maximum and minimum. This is the homework. Next. Guys, is this clear till over here? Please let me know in the chats. Guys, enough. Let's take a look. Let's take a look exactly at this point. You previously said when phase difference phi is equal to 0 degrees. Okay. Guys. You said when phi is equal to 0 degrees, at that point of time, we say constructive interference takes place. Already discussed in detail. Okay. You said when phi is equal to 180 degrees, at that point, we say destructive interference takes place. Already discussed in detail. There is no doubt in that. Sir, will the constructive interference take place only at 0 and 180? We say no. We say for constructive interference, guys, understand, for constructive interference, we say if phi is 0 degrees, cos phi will be 1. Constructive interference takes place. Sir, is it only at this angle? We say no. But the general formula, in general, we say phi is equal to 2n pi. If phi is equal to 2n pi, then constructive interference will take place. Now, guys, see. What I'm trying to say is that n value of n is 0, 1, 2, 3, 4, and so on. We say if phi is equal to 2n pi, if the value of phi is 2n pi, then we say constructive interference takes place. Now, guys, if I say value of n is 0, put 0 over here, phi will come out to be 0. We know at 0 constructive interference takes place. If we say value of n is, let's suppose 1, so it will be 2 into 1 is 2, it will be 2 pi. So we say at phi is equal to 2 pi, also constructive interference takes place. So cos 2 pi is 1. So we say constructive interference takes place at 0. 2 pi means 360 degrees. 4 pi, we say if n is 2, so 2 into 2 is 4, so 4 pi. So constructive interference takes place at 4 pi. So not only at 0 degrees, when phase difference is 0, but when phase difference is 0, 2 pi, like we say 0, 2 pi, 4 pi, okay, and so on. We say all of these, at all of these phase differences, we say constructive interference takes place. Next, when it comes to the destructive interference, what do you say? Sir, phi is equal to 180 degrees pi. Then we say cos phi is minus 1. Sir, is it only possible that constructive interference takes place at 180 degrees? We say no. Constructive interference, general formula is destructive interference. Destructive interference takes place at 2n minus 1 into pi, where n starts from 1, 2, 3, 4, and so on. Okay. Guys, let's suppose if n is 1, let's find the value of pi. So it will be 2 into 1 minus 1. 2 into 1 minus 1 into pi. So this is 2 minus 1. So it will come out to be pi. We know at theta is equal to pi, destruct interference takes place. Let's suppose if we put n is equal to 2. So 2 into 2, 2 into 2 is 4 minus 1 into pi. So it will be 4 minus 1 is 3. So it will be 3 pi. So at pi, at this angle, at 3 pi, 5 pi, 7 pi, we say destructive interference takes place. So general formula is this, that is 2n minus 1 into pi. And in this case, general formula is this, that is 2n pi. So at all of these values, destructive and constructive interference takes place. Okay. Now, we have discussed, guys, we have discussed the phase difference in case of constructive interference, 2n pi. We have discussed the phase difference in case of destructive interference, that is 2n minus 1 into pi. Let's talk about path difference in case of constructive and destructive interference. Like if we say two waves are meeting over here, okay? Two waves are meeting over here. Constructive interference is taking place. What is the value of phase difference? We say, you just studied, what is the value of phase difference? Sir, that is 2n pi. So 2n pi. Now one more question is, what is the value of path difference, sir? How much this has traveled, how much this has traveled, difference in the path. We know phase difference, if the two waves are meeting constructive interferently, then phase difference is 2n pi. What is the value of path difference? Path difference also will be there. We say path difference is n lambda. Path differences for constructive interference, path difference is n lambda. So my dear friends, if two waves are meeting constructively, so path difference will be n lambda. Okay. So my dear friends, in this particular case, if you put, we say if n is equal to 0, path difference in that case will be 0. So means both the waves have traveled the same path. If both the waves travel the same path, we say constructive interference takes place. We say if n is equal to 1, so delta x will come out to be lambda. At lambda also, path difference will take place. So we say if n is equal to 2, we say delta x will be equals to, that is 2 lambda, 3 lambda, so on. So whenever you see this path difference between the two waves, means constructive interference has taken place. Next, hey guys, why are you asking for the duration? It will take 5 hours, it will take. That's what I'm saying, 10 o'clock we'll finish this. Now destructive interference. Sir, this is the path difference between the two waves in case of destructive interference. This is the path difference between the two waves in case of destructive interference. That is 2n minus 1 into lambda by 2. Now guys, see. If you put the value of n is 1, so it will be 2 into 1, that is 2 minus 1 into lambda by 2. So 2 minus 1 is 1, so lambda by 2. So when path difference is lambda by 2, then destructive interference has taken place. If n is 2, we say 2 into 2 is 4, 4 minus 1, so 3 lambda by 2. When path difference is 3 lambda by 2, destructive interference will take place. If n is 3, path difference is 5 lambda by 2. So when path difference is 5 lambda by 2, destructive interference will take place. I hope this is crystal clear to each and every single student over there, ladies and gentlemen. Is this clear, guys? Next, Okay, we are done with this. Now let's move on to YDSE. Young's double. And let me just tell you, my dear friends, half of the Young's double slit experiment is already done. YDSE. Okay, now some remaining portion is over there. Some remaining portion is over there. Guys, see. What is this YDSE all about? YDSE means Young's double slit experiment. Young's double slit experiment. So we say this is the experiment which proved the wave nature of light. This is the experiment which proved the wave nature of light. This is the experiment which proves the wave nature of light. Yes. Now guys, what I want you to understand in this particular case, that is, let's suppose you take a light source over here. You take a light source over here. This is a light source. Light source. If this is a light source, we say light comes out of this light source, okay? And then, my dear friends, you place a hole over here, okay? Very thin hole. And then the light passes through this thin hole, or you consider this as a light source, okay? Don't consider here. Then, when you consider a light source over here, my dear friends, you place a cardboard or a sheet, something like this. You place a sheet and then cut this sheet with the razor or with the scissor over here. Okay. This is the top view I am saying. This is not the hole over here, guys. This is not the hole over here. We are cutting this with the cardboard or the sheet with the blade or something like that. Okay. A straight line. Now, this light will pass through these two narrow slits. These are what we call the slits. These are what we call the slits. Okay, these are called the slits. When the light comes and they pass through these narrow slits, and there is a screen placed over here. This is the screen. We observed that, guys, understand very carefully. We observed that when this light falls on the screen further, when it leaves the slits, when it falls on the screen, we observe these patterns are made over here. Okay. Bright fringe, dark fringe, bright fringe, dark fringe. I'll just mention over here. This is the bright fringe. Bright fringe. And this is the dark fringe. This is the bright fringe. This is the dark fringe. This is bright fringe. This is also dark fringe. So, my dear friends, this is the Young's double slit experiment. What do? We take a light source and we place a sheet or a cardboard, and then we cut this cardboard, okay, something like this, okay, with a thin narrow slits. This is a thin narrow slit. Then when the light passes through these narrow slits, we say on this screen, we observe that these bright dark patterns are made, bright and dark fringes are made. Now, how does it actually prove the wave nature of light? How does it actually prove the wave nature of light? Guys, what I want you to understand in this particular cases, let's suppose if we consider the light as a particle over here, we say, sir, particles will leave and they will fall directly at this spot. This light will only fall at this spot. So here particles travel in a straight line. So we say this particle comes, and we say these particles will fall over here. We say in that case, only this portion should be bright, only this portion should be bright. But instead we got bright dark even at the center point where no particle should actually reach, but that also seems to be bright. So can I say in this particular case, my dear friends, if you are considering the light as a particle over here, then this portion only should be bright, but that doesn't happen. And this portion only should be bright, but that doesn't happen. even I would say alternate bright dark spots are made. This is only possible when you consider the light as a wave. Because if light was a particle, only this portion would have been bright. Only this portion would have been bright. Because particle cannot travel like this, like this. It will go straight and falls over here, straight fall over here. So we say, so this clearly shows wave nature of light. This is what we call the interference of the waves over here. Interference pattern. Okay. This is called the interference pattern. Now, my dear friends, here a detail is mentioned. The light passes through the narrow slits and falls on the screen. And a bright dark pattern was made on the screen. If light was not a particle, if light was a particle, then this pattern was not possible. Then this pattern would have not been possible on the screen. Okay? It would have been bright over there only where slits are present. It would have been bright over there only where slits are present. Means here only bright, here only bright. If we consider light as a particle. Okay? But it proves the light behaves like a wave. That's why this pattern was made on the screen. That's why this pattern was made on the screen. This pattern is called the interference pattern. And so we say dark fringe is called. So this dark fringe is called minima and bright fringe is called maxima. So we say either you call this dark fringe as dark fringe or dark spot, or you can also call it we say minima. And this we call as maxima. This is minima and this is maxima. This is minima and this is maxima. Okay. Okay. Now, guys, understand over here. See. One more thing I just want to show you. One more thing I just want to tell you. We say the point, the spot where maxima is formed the spot where maxima is formed, constructive interference has taken place. Why? Because the point where maxima is formed, we say intensity of that point is large. Why? Because if you are saying this point is bright, bright means intensity is large. If intensity is large, amplitude is large. Amplitude is large where constructive interference takes place. So we say constructive interference has taken place. And another point, I'll just write the spot where minima is formed, the spot where minima is formed, destructive interference has taken place. Okay, because the point where dark fringe is formed, minima is formed, we say it has got less intensity, zero intensity. That's why it's dark. If intensity is zero, amplitude is zero. Okay, if amplitude is 0 means destructive interference has taken place. Okay. Now guys, tell me one thing directly now. We say when it comes to this interference pattern, this which is exactly at the center, this is what we call the central maxima. Central maxima, which is formed exactly at the center. And when it comes to the central maxima, it has got the maximum intensity, maximum brightness. So I can say this is the slit S1, this is slit S2. Light is passing through the slit. We say the central maxima is formed over here. Now tell me it is maxima. Can I say here constructive interference have taken place? Yes, constructive interference has taken place exactly over here. Then only we say maxima is formed, and maxima is formed in this particular case, and this maxima is called central maxima, and we say path difference in this case is 0. Okay, sir, why path difference in this case is 0? Because when it comes to the constructive interference, path difference can be 0, lambda, 2 lambda, 3 lambda. What is the general formula? That is n lambda. Already discussed. Okay. So if the path difference is, I'll just say, if delta x is equal to 0, we say lambda by 2, 0, lambda, okay, 2 lambda, 3 lambda, and so on. We say then we say at that points, on those spots, maximas are formed. Maximas are formed. Okay. So we say here, path difference, this is central maxima. And after central maxima, if you take a look over here, this is the central maxima. After central maxima, you have got this dark fringe. Then you have got this bright fringe exactly over here. Okay. Then again, you have got the dark fringe over here. Central maxima, dark fringe, bright fringe. This is called the central maxima, and this is called the first minima, first maxima. Okay. Second minima, second maxima. Guys, understand, this is first minima. First minima. This one is first maxima. Similarly, second minima, second maxima. Now, can I say, guys, when it comes to the destructive interference, the path difference can be lambda by 2, 3 lambda by 2, and we say 5 lambda by 2. So we say this is the path difference in case of minimas. This is the path difference in case of minimas. This is the path difference in case of minimas. This is the path difference in case of minimas. Now, when it comes to the central maximum, what is the path difference? 0. First minima, it is lambda by 2. First maxima, it is lambda. Second minima, it is 3 lambda by 2. Second maxima, we say it is 2 lambda. Then third minima, 5 lambda by 2, and so on. Now, I don't have to derive these once again because we have already derived this previously. Give me the signal in the chats if everything is crystalline clear. And guys, if you have not liked the session yet, I would want you guys to smash the like button as soon as possible. Okay. Now guys, let's move. So now guys, already discussed at delta x is equal to 0, lambda, 2 lambda, 3 lambda, maximas are formed. General formula is n lambda. So if you have to check where the maxima on the screen is formed, that is n lambda. Part difference is n lambda. And we say at delta x is equal lambda by 2, 3 lambda by 2, 5 lambda by 2, minimas are formed. So general formula is 2n minus 1 lambda by 2, already discussed. Let's suppose if somebody asks you, find the value of delta x, part difference for ninth minima. Guys, we say for ninth minima, what is the value of n? That is 9. And how to find the part difference for minima? For minima, it is 2n minus 1 lambda by 2. So I can say part difference will be 2n minus 1. We say lambda by 2. So 2 into n is how much? 2 into 9 minus 1. So this will be 2 into 9 is 18. 18 minus 1 is 17 lambda by 2. Okay, yes. Next we have got this over here. Distance at which the maxima and minimas are formed. Guys, let's suppose I have got the two slits over here. This is S1 and this is S2. Okay, you have got the two slits over here. That is S1 and S2. And in this particular case, we say light leaves from this slit. Okay, so we say it falls onto the screen, interference pattern is formed. We say distance at which the maxima. Okay, let's suppose, my dear friends, here a fringe is made. This is the central maxima. At this point. This is the central maxima. Sir, if there is a fringe which is made over here, either it is bright or dark, whatever it may be, at what distance from the central maxima it is formed? That y. So you will directly say y is equal to delta x, part difference, d by d. What is d? D is the distance between the slits and the screen, and small d is the distance between the two slits. Okay, so I say this is the distance at which fringe is made on the screen. This is the distance at which fringe is made on the screen from central maxima. Okay. 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 Now guys, if the fringe is made over here, we say this is the distance from the central maxima. Let's take a look at the question. Find the distance of fifth minima from the central maxima. If we say interference pattern is made on the screen, what is the distance of fifth minima? Like this is the screen over here. Sir, this is the fringes are made. What is the distance of the fifth minima from the central maxima? Guys. What is the distance? What is the formula? Y is equal to delta x d by d. So we say y is equal to delta x d divided by d. Now let's find the part difference for fifth minima. delta x for fifth minima. Delta x for fifth minima. Guys, when it comes to the delta x for fifth minima, how do we find the delta x? For fifth minima, 2n minus 1 lambda by 2. So I can write over here, this will be delta x is equal to 2n minus 1 lambda by 2. So n is 5. So 2 into 5 is 10. 10 minus 1. So that will be 9 lambda by 2. So I can say this distance will be simply 9 lambda d divided by 2d. Okay. Is this clear? Now guys, next you have over here, find the distance of seventh maxima from central maxima. Find the distance of seventh maxima from the central maxima. In this particular case, once again, y is equal to delta x d by d. Now, what is the value of delta x in this case, guys? For part difference for maximas, how do we find the part difference for the maximas? That is n lambda over here, n lambda. It's talking about the seventh maxima. So n is 7, so that will be 7 lambda. So y will be 7 lambda d divided by d. Okay, yes, yes, yes. Okay. Guys, I guess we need to take the break now, huh? Let's take a break. So we'll be taking the break till 7:35. Break till 7:35 p.m. Okay. This is a small chapter, okay? We'll finish early, like in 4 hours, 4 to 4.5 hours. We'll be finishing the entire chapter. So that's why I took the break now. Okay. Check. Now, guys, let's take a look exactly over here. Okay, let the people come and join. Then we are starting this session. See, guys. Now we have got the fringe width over here. Now we have got the fringe width over here. What does the fringe width actually mean? See. Let's suppose we have got the screen over here. Okay, this is the screen. Okay. And there is a fringe which is made exactly at this point. There is a fringe which is made exactly at this point. This is the fringe. What is the width of this fringe? That is what we call the fringe width. What is the width of this fringe is what we call the fringe width. Okay. Okay. Like this is, we say over here, I can say in this particular case, this is a fringe. And how do we find the width of the fringe? Simply you say lambda d divided by d. We don't have to go in the derivation. Simply, this is the width of the fringe. How wide the fringe will be. How wide the maxima and minima is going to be, that is lambda d by d. Okay. Then we have the angular fringe width. Guys, see. Let's suppose this is the fringe over here. We already calculated its fringe width, how wider the fringe is. But when it comes to the angular fringe width, I would want you guys to join this with over here at the bottom of this fringe. Okay. Then we say from this point to this point, you take a line. How much angle it is making with this? Guys, this is called the angular fringe width. This is called the linear fringe width. Okay. How much is the angular fringe width? Okay. Angularly, how wider it is? That is phi. And you can say, sir, this phi will be simply, that is lambda divided by d. This phi will be simply lambda divided by d. Because you can find this phi from tan phi, from this triangle. From this triangle, tan phi is perpendicular divided by base. Okay, that is beta. Beta is the linear fringe width, and base is, we say, this distance between the slits and the screen. What is beta? Beta we already got lambda d by d, and you can say lambda d divided by this d. D and d will cancel, so it will be lambda by d. So angular fringe width from now onwards will be saying that, sir, it is lambda by d, and this fringe width is lambda d by d, capital D, where d is the separation between the, slits and the screen. This is what we call the d, capital D, and this is the small d, distance between the two slits. If this is S1 and this is S2, distance between the two slits. Okay. Now, let's suppose we have got a question exactly over here. In a Young's double slit experiment, if the separation between, if the separation between the slits is halved, we have got a Young's double slit experiment. So this is S1 and this is S2. Separation between the slits is D. It says that if D is halved, okay, and distance between the slits and the screen, this is the screen and this is capital D. This is capital D. And this is doubled. Guys, first of all, tell me what is going to be the fringe width in this particular case. Beta is equal to lambda D divided by D. Now it says that if separation between the slits is halved, it says that this D dash becomes D by 2. And if the separation between the slits is halved, okay, D dash is equal to D by 2. Okay, D dash is equal to D by 2. And this D, separation between the slits and the screen is doubled. We say D dash becomes 2D, capital D. So this distance is doubled, this distance is halved. What is going to be the fringe width? We say, sir, new fringe width will be beta dash is equal to lambda D by D. Lambda is wavelength. D divided by D. D is, we say, sir, 2D divided by, this D is D by 2. So take it over here. So it will be 4 lambda D divided by D. What is lambda D by D? Lambda D by D is beta. So we say this beta dash will be, that is 4 times of beta. Okay. Beta dash will be 4 times of beta. Okay. Next we have, in a Young's double slit experiment, blue-green light of wavelength lambda is equal to 500 nanometers. Okay, is used. We say wavelength of light is given as 500 nanometers. If you convert this into meters, you say 500 into 10 raised power minus 9. 500 into 10 raised power minus 9. Whenever you convert something from nanometers to meters, you multiply with 10 raised power minus 9 in that particular case. Okay? Yes. Okay? And then, my dear friends, over here, the slits is 1.2 mm apart. So D is given as 1.2 mm. 1.2 mm, you can write 1.2 into 10 raised power minus 3 meters. Because if you convert mm into meters, multiply with 10 raised power minus 3. And the viewing screen is 5.4 meters away. Viewing screen is distance between the slits and the screen. So that is capital D is given as 5.4 meters. Find the fringe width. You guys are supposed to tell me the fringe width. Guys, can I say when it comes to the beta, that is lambda D divided by this D. Okay. Now what is lambda? Lambda is given as 500 into 10 raised power minus 9. What is the value of D? D is given as 5.4 divided by, what is the value of small d? That is 1.2 into 10 raised power minus 3. Okay. 1.2 into 10 raised power minus 3. So solve it. It will come out to be that is 2.25 into 10 raised power minus 3 meters. This option A. Okay, let's take a look at this. What happens to the fringe width? What happens to the fringe width, guys? What happens to the fringe width when the blue color of light is replaced with the red color? Guys. In the ray optics, I have told you V, I, B, G, Y, O, R. When white light is split into 7 different colors, what are those 7 different colors? Violet, indigo, blue, green, yellow, orange, red. It says that what happens to the fringe width when blue color of light is replaced with the red light? When blue is replaced with a red light. Guys, always remember, as you move from violet to red, we say in this direction, we say a lambda increases. Means wavelength of red is greater than wavelength of violet. So lambda increases. Now what happens to the fringe width? Guys, we say beta is equal to lambda d divided by d. If wavelength increases, guys, if you replace blue light with the red light, we say lambda will increase. If lambda increases, we say this beta increases. Okay, so fringe width also increases. Because if you replace blue light with the red light, means lambda of red is greater than lambda of blue. So lambda will increase. If lambda increases, we say fringe width will increase. One more question. In a Young's double slit experiment, the fringes are formed at 1 meter from the double slits of separation this. So in a Young's double slit experiment, what is given is that Fringes are formed at 1 meters from double slits. Means capital D is given as 1 meters. Distance between the slits and the screen is given as 1 meters. Okay. From double slits of separation. Separation between the slits is given as 0.12 mm. 0.12 mm. Calculate the wavelength of light used. Calculate the wavelength of light used if the distance of third bright band, okay, from the central screen is, so basically it says that if this is the screen over here, this is the central maxima, this is the first maxima, second maxima, third maxima. It says that you have to find the value of wavelength of light, what is lambda, used if the distance of third bright fringe, this is third maxima. If the distance of third maxima from the central maxima, that is y is given as 1.5 centimeters. It is centimeters. Okay. So what does this y actually mean? I have discussed over here. It is the distance, no, not this one. Here, yeah. It is the distance of the fringe from the central maxima, that is y. And what is the formula? Delta x d divided by d. Okay. Delta x d divided by d. In this case, we say y is given as 1.5 centimeters. So I can say as y is equal to delta x d divided by this d. Now tell me one thing. It is saying that if the distance of third bright band for maxima, what is delta x? Guys, what is the path difference for the maxima? Already discussed. Path difference for the maxima is n lambda. So here I can put directly n lambda in this particular case. So for bright fringe, for maxima, delta x is equal to n lambda. So can I say in that case y will come out to be, that is n lambda d divided by this d. You are supposed to find lambda. Take it over here. So it will be yd is equal to n lambda d. So lambda will come out to be yd divided by this nd. Now tell me one thing, my dear friends. So how do we find the value of this lambda? Lambda is equal to, what is the value of y? Y is 1.5 centimeters. 1.5 into 10 raised power minus 2. Okay. Let me write over here. So I can say this lambda will be y is 1.5 into 10 raised power minus 2. Okay. D, that is 0.12 mm. So this is 0.12 into 10 raised power minus 3 into 10 raised power minus 3. Okay. Divided by nd. What is n? We are talking about the third maxima. So n is 3. N will be 3 over here. 3. And what is the value of d? Separation, that is 1. So it is 1. Okay. Find out the value in this particular case. This will be 10 raised power minus 5. Okay. Over here and divided by 3. Okay. So I guess you are supposed to find this in the angstrom over here. Yeah. Okay. So solve this and then check it. How much is the answer that is coming out to be in this particular case? Next, let's take a look over here. In a Young's double slit experiment, the distance between the slits is 1 mm. So D is given as 10 raised power minus 3 meters. 1 mm means 1 into 10 raised power minus 3. And screen is 25 centimeter away. So means D is given as 25 into 10 raised power 25 into 10 raised power, we say into 10 raised power minus 2 meters. If the wavelength lambda is given as 6000 angstrom, so 6000 into 10 raised power minus 10 meters. Because if you convert angstrom into meters, you multiply with 10 raised power minus 10. What is the fringe width? Fringe width is simply lambda D divided by D. Just you have to put the values and get the fringe width. Okay. Same question. In a Young's double slit experiment, blue-green light of wavelength 500 nanometer. So lambda in this case is given as 500 into 10 raised power minus 9 meters because it's in the nanometer convert. And slits D is given as 1.2 into 10 raised power minus 3 meters. And this is given as 5.4. So capital D is given as 5.4 meters. You guys are supposed to find the value of beta. Let's talk about in this particular case. We say non-standard YDAC. Non-standard YDAC. What is non-standard YDAC? Guys, see. Let's suppose you have a Young's double slit experiment and you place this Young's double slit experiment in a medium. Previously, you performed this Young's double slit experiment in air. Now, I would want you guys to perform the Young's double slit experiment in a medium. Okay. Now, guys, when you perform this Young's double slit experiment in a medium, in that particular case, what you are supposed to do is, I say, you take the two slits over here, you take a screen over here, okay? We say light will leave from the slits and the central maxima fringes are made, okay? But when it comes to the refractive index of this is mu, okay? And wavelength in this particular case, guys, we say wavelength in this medium will be wavelength in air divided by mu, refractive index of this medium. I have explained previously what the refractive index is all about. Now, guys, we say for this medium, wavelength of light is lambda by mu. Now, see. The position of the maxima and minima will be, sir, if I say at this point maxima is formed, what is the position? What is the distance from central maxima to this? When it comes to the normal YDAC over there, what was the position of the fringes? Position of the fringes was normally, what is the Y distance? Delta X D by D. Sir, what happens to the position of the maximas and minimas when you perform this experiment in a medium? We say, for maxima's position will be n lambda d by d because previously, guys, what was the formula previously? We say formula previously was y is equal to delta x d divided by d. For maximas, we were saying, sir, putting the delta x value over here, path difference over here. Okay. Now, in this particular case, when it comes to the path difference for maximas, recently I have told you what is the path difference for maximas n lambda. What is the path difference for minima? 2n lambda, 2n minus 1 lambda by 2. So here you will be putting simply in this particular case, over here. Just a second, guys. So you will be putting, sir, for maxima, this y will come out to be, that is n lambda d divided by d. Sir, what is difference over here? Instead of lambda, you will be putting over here lambda of this medium. Wavelength of this light in this medium, n lambda medium d divided by d. What is the lambda medium? That is lambda by mu. So you will be writing n. Instead of lambda medium, you will be putting lambda by mu. where mu is the refractive index, d divided by d. This will come out to be the position of the maxima in non-standard YDAC. Similarly, in case of, we say minima, we were putting over here y minimum, position of the minima. Instead of delta x, I'll be writing part difference 2n minus 1 lambda d divided by, we say 2d. Okay, so here instead of lambda, I will be putting lambda of this medium, and lambda of this medium will be lambda divided by 2 over here. Okay, lambda divided by mu over here, lambda divided by mu over here. So this will be the minimum. This will be the position of the minimum in the non-standard YDAC. What I'm doing in this particular case is simply, I'm saying here I'll put lambda medium. So instead of lambda medium, you will be writing lambda divided by mu. Rest everything is same. Okay. Sir, what about the fringe width? Guys, what was the value of fringe width? Fringe width for beta is equal to lambda d divided by d. But here you will be putting lambda of this medium, because lambda changes, fringe width changes, lambda of this medium d divided by d. Now instead of lambda medium, you will be putting lambda by mu d by d. This will be the fringe width in this particular case. I hope this is crystal clear to each and every single student out there. This is crystal clear to each and every single student out there. Next. Slab in front of the slit. Guys, let's suppose you have got slit S1, and in front of the slip you have placed a slab, and refractive index of this slab is mu. Okay, refractive index of this slab is mu. Now when you place like this is the slit in front of the, this is the slit in front of the slit, you are placing the slab over here. So in the next here you do not place any sort of slit. We say if you in a YDAC, Young's double slit experiment, if you place the slab, glass slab in front of the slit, central maxima will shift in the direction in which slab is inserted. If the slab is inserted from the upper side, central maxima will shift in the upper direction. If the slit is placed in front of this slab, then the central maxima will shift in the lower direction. Okay, but when it comes to the fringe width remains the same. Okay, now sir, if you are saying in this case central maxima will shift, how much will be the shift of central maxima? How much central maxima will shift from its original position without slab? So shift in the central maxima. Okay, how much? If initially it was made over here, now it is made, how much is this shift in the central maxima? That is d. D is the separation between the slits and the screen. Mu minus 1, where mu is the refractive index. Refractive index of the slab. Okay, and what is T? T is the width of the slab. Okay, D mu minus 1 into T divided by D. And what is this D? D is the separation between the two slits. D is the separation between the two slits. And number of fringes made over here will be mu minus 1 into T divided by lambda. How many number of fringes will be formed exactly? So this one and this one. So this is, we say, slab in front of the slit, and this is non-standard YDAC. Non-standard YDAC. Is this clear? Is this clear? Okay. Okay. So non-standard YDSE slab in front of these slits. Okay, great. Now guys, let's move on to the another topic, that is what we call the diffraction. That is what we call the diffraction. That is what we call the diffraction. See guys, what does the diffraction actually mean? What does the diffraction actually mean? Diffraction means creating this fringe pattern with the help of a single slit. This is what we call the single slit diffraction also. Like in case of YDS, Young's double slit experiment, how many slits we were taking over there? We were taking 2 slits. But when it comes to this, here we take only 1 slit. Here we take only 1 slit, single slit. Okay. So in this particular case, we take only 1 slit. Like guys, this is the slit over here. This is the light source. Light source is passing through the slit, and we say on this screen interference pattern is formed. Like I'll show you. Like this, like this. This is also the diffraction. The door is opened, okay? So here, the light is passing through this slit, and this diffraction pattern is formed. This is called the diffraction in real life. And in the example, you can see over here, you have got a slit over here. Light rays are coming, light waves are coming. When it is passing through the slits, on the screen, you can clearly see the fringe pattern is formed. This is the maxima, bright. This is minima. This is maxima, this is minima. Okay. Now guys. In this particular case, what is the difference between this pattern and the YDSE pattern? The difference over here is, in this case, this central maxima is bigger. This central maxima is bigger. It is large. Okay. And then, if this is the central maxima in this particular case, I would want you guys to focus over here. This central maxima has got the large intensity, maximum brightness. Okay. Then you have got this. As you move away from central maxima, we say intensity decreases. Then you say this has got less intensity, less, it keeps on decreasing. Similarly, this is the first maxima from the upper side, second maxima from the upper side, third maxima. This is the first minima, second minima, third minima, fourth minima. Similarly from the lower side also. Okay. And you can clearly see intensity is large for this one, then intensity decreases, and intensity becomes 0. Similarly, in this particular case, this is the diffraction pattern. Diffraction is interference only. It is YDSE only, but it is, we say, interference at single slit. Single slit. Okay. 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 Now, my dear friends, in this particular case, what we are supposed to study is diffraction at the single slit. This is the actual diagram that we need to understand over here. Okay. See guys, what does diffraction at single slit mean? This is a light source. Light is coming from the light source. Okay. And here, this is the slit. This is the opening of the slit. Sir, it looks bigger. In reality, it is very small, but this is the zoomed view over here. This is the zoomed view. And how much is the width of this opening? That is given as A. A is the width of this opening. Okay. Now, light rays, first light ray is leaving. Okay, that falls exactly at this point. Another light ray is leaving and that falls at this point, and another light ray. So the point where these light rays are actually meeting, where these waves are meeting, we say interference takes place over there. We say fringe will be formed over there. So like another light ray is passing, okay, another light ray is passing, okay, these are meeting over here and they are meeting at the central maxima. Here also interference is taking place and fringe is being made over here. Fringe is being made over here. Fringe is being made over here. So how fringes are made? When two light rays or more than two light rays, waves intersect at any particular point, we say fringe is made at that point. Okay. Now, this is the slit. Distance between the slit and the screen. This is the screen is given as capital D. Given as capital D. Okay. Yes. Is given as capital D. Okay. I hope this is crystal and clear till over here. Now, my dear friends, what we need to understand in this one, as I have explained all of these points, we say A is the size of the opening, D is the distance between the slit and the screen. Okay. Okay. Now, guys, one thing I just want to say, let's suppose there is a light ray which goes and falls exactly over here. Another light ray goes and falls exactly over here. Draw a line. This is perpendicular. What I'm saying is that a light ray falls at this point. Another light ray falls at this point. If you draw a line over here, don't you think that this much is the extra distance traveled by this light ray? If I make it over here, let's suppose I'm making it something like this. I'm making this another ray something like this. Okay. Now you draw this perpendicular exactly at this point. Can I not say in this particular case, this much is the distance, extra distance traveled by this light wave? Yes. If this much is the extra distance traveled by this light wave, sir, how much is this distance? See, guys, this is A. This angle is over here. Let's suppose theta, it is given. This will be A cos of theta and this will be how much? A sin theta. Can I say delta x path difference in this particular case will be A sin of theta? Yes. Path difference is actually how much is the difference in their paths. So if this is A cos theta, this is A sin theta. So path difference is A sin theta. Okay. Okay. Now guys. Since we said path difference is A sin of theta. See. Let's suppose on this screen, maxima and minima is formed. On this screen, let's suppose this is the, on this screen, this is the central maxima. This is the central maxima. Okay. And this is the first maxima. This is the second maxima over here. Similarly, first maxima, second maxima over here. Okay. Now, my dear friends, what is the path difference for maxima? For maxima, path difference will be. Basically, what I'm trying to say is that when the light waves meet at this point, so when the light waves meet at this point, there will be the difference in the paths. Like in this case, these two light rays are meeting over here. How much is the difference? A sin theta is the path difference. Now, if I'm saying, guys, at this particular point, if I'm saying maxima is being made, maxima is formed, what will be the path difference? In that case, when it comes to the maxima, we know path difference is A sin theta. When it comes to the maxima, you say this will be the path difference, that is 2n minus 1 lambda by 2. Sir, when it comes to the Young's double slit experiment, YDSE, what was the path difference for the maxima? Sir, here path difference for maxima was n lambda. Yes. And path difference for minima was 2n minus 1 lambda by 2. But in this particular case, in case of diffraction, we say for maxima, what will be the path difference? I am saying the path difference in this case will be 2n plus 1 lambda by 2. 2n plus 1 lambda by 2. So this will be the path difference. If I am saying, sir, at maxima two light waves are meeting, what will be the path difference between the two? This will be the path difference. N can be 1, 2, 3, 4 and so on. Let's suppose if we are talking about the first maxima, what will be the value of A sin theta? Guys, we'll be saying 2 into 1 is 2. 2 plus 1 is, so that will be 3 lambda by 2. Path difference in that case is 3 lambda. Similarly, second maxima, third maxima you can find out. Now guys, you have got angular position of nth maxima. See guys, what I'm saying is that what I'm saying is that in this particular case, see, I'm saying this is the, let's suppose, opening. Okay. In this particular case, sir, this light wave is meeting, this light wave is meeting, okay, and maxima is formed. If maxima is formed, sir, how much is the path difference? This much is the path difference. Okay. This is delta x. And what is the value of delta x? That is, this is a sine theta. A sine theta. And what is the value of this a sine theta? 2n plus 1 lambda divided by 2. Now angular position. How do we define the angular position actually? Guys. See. How do we define the angular position? If I am supposed to write the angular position over here, see. We say this is the line with the central maxima. At what angle this fringe is actually made? That is what we call the angular position. Angular position of the nth maxima, it is saying. Angular position of the nth maxima. And let's suppose if I say n is equal to 1, means first maxima. If I say n is equal to second maxima, n is equal to 3, third maxima. Like you discussed, angular position of the maxima over here. Angular position. Okay, this was angular fringe width. Okay, wait, where is it? Where is it? Okay, let me show you here only. Angular position means at what angle it is actually formed. At what angle it is actually formed. Okay? At what angle it is actually formed. Like here. This theta. If you are talking about this fringe, at what angle, what should be the value of this theta? This theta at which the fringe is present. Angular position. I hope you got it. Sir, here theta is 0. If you keep on increasing, sir, at 30 degrees, this fringe is present. At 30 degrees, this fringe is present. So means angular position is 30 degree. How can we find the value of theta in this case? Guys, see. Angular position of nth maxima will be. Guys, in this case, this theta is very small. If theta is very small, so we say sine theta is equal to theta. If sine theta is equal to theta, you can clearly say, it is a sine theta. You can clearly say this a will go in the denominator over here. So sine theta, see, from here we can write this sine theta will come out to be 2n plus 1 lambda by 2a, because this a will go over here. Okay. If theta is very small, so theta will come out to be 2n plus 1, okay, lambda divided by 2a. This will be the value of we say theta, angular position. Similarly, my dear friends, position of, this is maxima. Okay, let's talk about the position of minima. Guys, for once again, if I say at this particular point, when we talk about this fringe, this is minima. Sir, if two light waves are meeting at this particular point, so what is being formed? Minima is formed. So what is the path difference between the two waves? That is delta x. And this is a sine theta in this case also. And what is the value of this delta x or a sine theta? It will be n lambda. So for minima, in case of diffraction, path difference is n lambda. Okay. Path difference is n lambda. Now guys, and when n is equal to 1, so a sine theta path difference will be lambda, 2 lambda, 3 lambda, and so on. Similarly, here, angular position. How do you find the angular position of nth minima? You can say, sir, sine theta is equal to, take this a over here, n lambda by a. So theta will be n lambda by a. So this is the position at which minima is placed angularly. Okay, like I say, at this particular point, if this is minima, what is the value of this theta? That will be the angular position of the minima. Okay. 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 Now guys, one more thing I just want to say. You got the position, angular position. Okay, that is fine. Now, if somebody asks you, what is the position of the maxima from the central maxima? Like. Guys, understand this very carefully. If I'm saying this is the central maxima over here, central maxima, and this is a maxima formed exactly over here, nth maxima. Now, if you join from this point, from center till this point, this is what we call theta. That is the angular position. This is angular position. Angular position. Then you have got the linear position. Sir, how much is this distance? Why? How far this maxima is produced from central maxima? That is 2n plus 1 lambda into d divided by 2a. Lambda is what? Wavelength. D is distance between the separation and the slits. A is size of the opening. Similarly, in this case, if I make the same diagram over here, okay, so let's suppose this is over here central maxima, and here it is minima, nth minima. Here it is nth minima, and from this point till over here, this is called the angular position theta. And this will be y. Position of this nth minima from the central maxima, that is y. Okay, so for minima, angular position is this much, path difference is this much, angular position is this much. Okay, and when it comes to the linear position, that is n lambda d divided by a. Guys, is this crystalline clear? That's all about diffraction. There is nothing, no other formula when it comes to the diffraction. Okay, one more thing I just want to mention, but till over here, is this crystalline clear? Please let me know in the chats. Is this crystalline clear? Is this, guys, tell me in the chats with the fire emojis. Great. Now guys, next chapter will be basic mathematics and vectors. Take a look over here, guys. Let's talk about the central maxima. let's talk about the central maxima. Let's talk about the central maxima. Guys, when it comes to the central maxima in case of the diffraction, it has got the large intensity and it is more wider, it is having the more width. Okay. Now we say central maxima is more wider with large intensity. This is the central maxima with the large intensity in this particular case. Okay. And when it comes to the linear width of central maxima, how much is this width? How much is the linear width of central maxima? This much. That is 2 lambda d by A. D is the separation between the slits and the screen. A is the size of the opening, size of the slit. Okay, this will be the linear width. When it comes to the angular width, my dear friends, that is 2 lambda by A. 2 lambda by A. Angular width, okay, angular width. How much is the angular width? Okay, if I'm saying this is the central maxima over here, how much is this angular width? Angular width. Okay, this much, angular width. This much. Angular width of central maxima. And that is 2 lambda divided by A. Where A is the size of the opening, D is the separation between the screen and the slit, lambda is the wavelength. That's it. That's it. And this is the intensity distribution curve. So the central maxima has got the large maximum brightness, maximum intensity. Then intensity decreases. Okay. Then intensity keeps on decreasing over here. Okay. You can clearly check in this particular case. Okay. And guys, you see over here, when path differences lambda over their intensity becomes 0. It is touching the curve. It is touching 0 over here. So means this is minima over here, minima over here, minima over here. And this point is maxima, maxima, maxima. Okay. So I hope you are getting, and this is the central maxima, highest intensity, first maxima, second maxima, first minima, second minima, third minima, and so on. And so on. And you can check over here. Okay. Diffraction pattern due to a single slit consists of central maxima flanked by alternate minima and secondary maxima. If I naught be the intensity of central maxima, if I naught is the intensity of central maxima, then the intensity of first 3 secondary maximas will be, guys, for central maxima it is saying intensity is I naught. For first maxima it is I naught by 22. For second maxima it is I naught by 62. For third maxima it is I naught by 121. Just directly remember this. Directly remember this. Okay. The diffraction fringes are of unequal width and unequal intensities. When it comes to the diffraction fringes, they are of unequal width and unequal intensities. Okay. Let's take a look at the question over here. Light of wavelength 6000 angstrom. Lambda is given as 6000 angstrom. So if you want to convert, it will be 6000 into 10 raised power minus 10. 6000 into 10 raised power minus 10. Okay. Is incident normally on a slit of width 2 into 10 raised power 2 into 10 raised power 5. 24 into 10 raised power 5. Means value of A is 24 into 10 raised power minus 5 centimeters over here. Minus 5 centimeters over here. Okay. Find out the angular position of second minimum from the central maximum. We have to find the angular position of second minimum. Guys, see. When it comes to the angular position of second minima, this is the linear position of nth minima. Okay, that is n lambda d by A. When it comes to the angular position, that is theta is equal to n lambda by A. Angular position of nth minima, n lambda by A. For second minima, it is 2 lambda by a. For third minima, it is 3 lambda by a. For we say theta is equal to n lambda divided by a. Just put over here. We say in this particular case, theta is equal to n lambda divided by a. Okay. And what is the value of n? Value of n in this particular case is second. Why? Because they have asked for the second minima in this particular case. Okay. Guys, is this clear? Is this clear? Okay. Now you need to put the values over here. So you will be writing over here value of n is 1. Sorry, value of n, it is talking about find out the angular position of second minimum. So it is 2. What is the value of lambda? That is 24 into 10 raised power minus 5. It is in the centimeters. If you convert centimeters into meters, you multiply it with 10 raised power minus 2. It becomes meters. Divided by a. What is the size? Oh, sorry. It is lambda. So it is lambda is 6000 into 10 raised power minus 10. Divided by, what is the value of a? 24 into 10 raised power minus 5 into 10 raised power minus 2. Solve it and check what is coming out to be the answer in this particular case. Okay. I guess theta should be equal to the 30 degrees over here. Okay. So this comes, solve it and theta will come out to be equal to 30 degrees. So angular position means at what angle the second minimum will be, that is 30 degrees. You have got this. Light of wavelength lambda is given as 6328 angstrom. Okay. So you can say this is 6328 into 10 raised power minus 10 meters. Is incident normally on a slit of width A is given as 0.2 into 10 raised power minus 3 meters because it is given in the mm. Calculate the angular width of central maxima on a screen of distance 9 meters. So D is given as 9 meters. You have to find the angular width of central maxima. Guys, when it comes to the angular width of central maxima, we say this is the linear width of central maxima, and then angular width would be, for central maxima, it is 2 lambda divided by A. Angular width will be 2 lambda divided by A of central maximum. So theta will be 2 lambda divided by A. So 2, what is the value of lambda? 6328 into 10 raised power minus 10 divided by, what is the value of A? 0.2 into 10 raised power minus 3. Okay. Solve this and check it how much it is coming out to be. Okay. So check it. It is 0.36. I guess it is coming out to be degrees. Check it later on. Okay. Next. A screen is placed 2 meters away from a single narrow slit. Okay. So D is given as 2 meters. Screen is placed 2 meters away from the single narrow slit. Calculate the slit width. We are supposed to find the value of A. If the first minimum lies 5 mm, on either side of the central maximum, means if this is the screen, it says that this is the central maximum. It says that if the first minimum, let's suppose this is the first minimum over here. This is the first minimum. If the first minimum lies at 5 mm from the central maximum, means value of y is given as 5 mm. I'll show you over here. If the fifth minimum lies at the 5 mm, linear distance of fifth minimum. No, here it is. Yes. Guys. This is the minimum placed over here, created over here. From the central maximum to the minimum, how much is the distance, linear distance? That is y. And it is given as y is equal to n lambda d divided by a. This is the position of the nth minimum from the central maximum. This is the linear position and this is the angular position. Y is equal to n lambda d divided by a. I'll use the same formula over here. We say y as position of nth minimum from central maximum. Y is equal to n lambda d divided by a. Okay. Incident wave has a wavelength of lambda is given as, and this we can write 5 into 10 raised power minus 3 meters. When it comes to the lambda, it is coming out to be 5000 angstrom in 10 raised power minus 10 meters. Okay. So over here, you will be writing y is equal to n lambda d divided by a. We'll be writing y is equal to, okay, what you are supposed to find a will be n lambda d divided by y. A will come out to be, what is the value of n? N is 5 because it is talking about the fifth minimum. Lambda is given as 5000 into 10 raised power minus 10. D in this case is given as, that is 2 meters divided by y. What is the value of y? 5 into 10 raised power minus 3. Solve it and check what is going to be the answer. Solve it and check what is going to be the answer. Okay. Okay, it's 1 over here. It's 1 because it's talking about the first minimum. It is 1 over here. 5000 into 10 raised power minus 10 into 2 divided by this. 2 into 10 raised power minus 4. Okay. Yes. 2 into 10 raised power minus 4. Next. We are almost done with the chapter. By 9 o'clock, before 9 o'clock, we'll finish the chapter. Before 9 o'clock, we'll finish the chapter. A plane wave front has a wavelength of 6000 angstrom. Lambda is given as 6000 angstrom into 10 raised power minus 10 meters. Is incident upon a slit of 0.2 mm. So A is given as 0.2 mm. 0.2 mm. So that is 0.2 in 10 raised power minus 3 meters. Okay, on a is formed diffraction pattern to be obtained and screen is 2 meters away. D is given as 2 meters. Width of the central maximum. What is the width of the central maximum, guys? It is asking for the linear width in this particular case. See? When it comes to the width, that is 2 lambda d divided by a. 2 lambda d divided by a. We are supposed to find the width of the central maximum. That will be 2 lambda d divided by a. So this will be 2. What is the value of lambda? 6000 into 10 raised power minus 10. What is d? D is given as 2 divided by a. A is given as 0.2 into 10 raised power minus 3. Check it, what is going to be the answer. Next, a plane wavefront of this. Okay, once again the similar type of question. Plane wavefront of wavelength 6000 angstrom is incident upon a slit of 0.2 mm width. Okay, what is the width of central maximum? 0.22. Oh, same question. Next, monochromatic light of wavelength Again, the same question, guys. Your wavelength is given as 580 nanometer. So if you convert into the meters, we say 10 raised power minus 9 into 10 raised power minus 9 meters. Width is given as, A is given as width of the slit 0.3 into 10 raised power minus 3 meters. Screen is 2 meters away. D is given as 2. Width of the central maximum 2 lambda D divided by A. Put the values and get the answer. Okay. Light of wavelength 550 nanometer falls on a slit of this. The angular position of the second minima. Okay. Guys, here lambda is given as 550 nanometers. This is the wavelength of light. You can say it is 550 into 10 raised power minus 9 meters. Something like this. Okay. Falls normally on a slit of width 22.22 in 10 raised power. Okay. A is given as 22 into 10 raised power minus 5 centimeters into 10 raised power minus 2 meters. Okay. The angular position of second minimum. We are supposed to find angular position of second minimum. How do we find the angular position of second minimum? Guys, tell me. Angular position of second minimum. Here it is minimum. And what is the angular position of minimum? That is theta is equal to n lambda divided by A. Theta is equal to n lambda divided by A. Let me put over here. So I can say in this case theta is equal to n lambda divided by A. Okay, n is 2 because it is talking about second minimum. Lambda is given as 550 into 10 raised power minus 9 divided by A is given as 22 into 10 raised power minus 5, 10 raised power minus 7. Solve it and check what is the answer. Next one. Angular, okay, this is the angular width of central maxima. This is, I'll give you as homework. Okay. What else? What else? This also is homework. Let me know the answer of these two questions in the comments later on once I end this session. With this, we are done with the diffraction also. With this, we are done with the diffraction also. Now we have got the polarization of the light. We have got the polarization of the light. We have got the pole. Is this clear till over here? Give me the signal in the chats, guys. Wave optics is a very small chapter. Now guys, take a look over here. What does polarization of light actually? Guys, if you are not like the session yet, I would want you guys to smash the like button, okay? See? We say light is an electromagnetic wave in which electric field and magnetic field vectors vary sinusoidally, perpendicular to each other. Guys, see. When we talk about wave on a string, okay, let's suppose this is a wall over here. You are connecting a rope to this wall, okay? And then you start creating the wave over here. That's wave on a string. What is the thing that oscillates over here? It is the particle which oscillates. Like first particle of this string oscillates, it goes up and down. Then it transfers the energy to the next particle. Then it goes up and down. Then next particle up and down. Similarly, wave is formed actually over here. When it comes to the wave on a string, what is the thing which oscillates? It's the particle oscillates. Okay, particle oscillates. So in case of a wave on a string, what is the thing which oscillates? That's particle is oscillating over here. Okay. But when it comes to the electromagnetic wave, we say light is a wave, but which wave? Electromagnetic wave. In case of an electromagnetic wave, directly remember, it is electric field and magnetic field which are oscillating over here. Okay. It is electric field and magnetic field which are oscillating. Like you can see, this is the electric field. You can say something like this. And this would be magnetic field over here, something like this. Okay. Consider here it is the electric field only, but in reality, we say it is like if I make the graph over here, if I make the electromagnetic wave over here, if you say this is the electric field oscillating, and you can say this is the magnetic field oscillating. Something like this, bro. Okay. Like you understand from this example. See. It is difficult to make in 3D. So here you say this electric field, this is magnetic field. This is electric field, this is magnetic field. Okay. So like it is mentioned, light is an electromagnetic wave in which electric field and magnetic field vectors vary sinusoidally. Sinusoidally means something like this. Okay. Perpendicular to each other, as well as perpendicular to the propagation of wave. Guys, see. If electric field is vibrating in the y direction, magnetic field is vibrating in the x direction, if electric field is vibrating in the y direction, magnetic field is vibrating in the z direction, wave is propagating in the x direction, wave is following the direction in x. This is the magnetic field, this is the electric field, this is the magnetic field, and this is the direction of the wave. This is the direction. 3 dance moves. Okay. This one, and this one. This is the electric field, this is the magnetic field, and this is the wave. This is the wave. All the three are mutually perpendicular to each other. Okay. The magnitude of electric field vector is much larger as compared to the magnitude of magnetic field vector. Magnetic field is large as compared to the, electric field is large as compared to the magnetic field. Okay. Thus, we prefer to describe light in terms of electric field oscillations. So, we neglect magnetic field. We consider only electric field vectors in light. Okay. Then we say, in ordinary light, the electric field vectors are distributed uniformly in all possible directions. Like over here, my dear friends, if you consider this as ordinary light, or we say unpolarized light, sir, this electric field is in this direction, in this direction, in this direction, okay? Electric field is vibrating in all possible directions. Sir, you said it is only in the Y. Yes. You say this in Y, this in X. But we say magnetic field is very small, so we neglect this magnetic field. We say it is only electric field which is vibrating in all possible directions. So now, this is also electric field oscillating in this direction. This is also electric field oscillating in this direction. Okay. In ordinary light, the electric field vectors are distributed uniformly in all possible directions, perpendicular to the direction of propagation of wave. Such a light is called unpolarized light. We say here, in this particular case, this is the unpolarized light, because in case of unpolarized light, electric field is vibrating in X, in Y, X, Z, in all possible directions. Then, my dear friends, you place a polarizer over here. This is a polarizer. This is a polarizer, which polarizes the light, which I'll teach you both Brevister's law also, Malus law also. Chill, take a chill pill. Okay. So we say you place a polarizer over here. What does the polarizer do? It will polarize the light. Guys. This polarizer basically allows only vertical component of the electric field. It allows only that electric field which is vibrating in the Y direction, This X component or any other component, it is cancelling. If the electric field is vibrating in this Z, it is cancelling that. This light is called the polarized light. So when we talk about the unpolarized light, in case of unpolarized light, electric field is vibrating in all possible directions. When you place a polarizer, it will allow only that electric field which is vibrating in a unique direction, like in Y direction here. In some other cases, it will allow only X portion only, this X component of electric field only. Here it is allowing Y. So this is called the polarized light. Okay. Now guys, this is unpolarized light. Electric field vectors in all possible directions. Okay. Here intensity of light is I naught. Yes, sir. Now when it enters the polarizer, this is polarizer. Now this polarizer is cancelling this electric field, this electric field, this electric field. It is allowing only this vertical electric field, this. And when light leaves the polarizer, we say its intensity becomes I naught by 2. If previously it was I naught, now it becomes I naught by 2. Okay. Then we place another polarizer over here. That is what we call the analyzer. So when you place the analyzer over here, my dear friends, and this analyzer, this is the axis, vertical axis. This analyzer is placed at an angle of what? Phi with the axis of the polarizer. If this is the axis of the polarizer, previous polarizer, you tilt this analyzer at an angle of what? Phi. Now when this light leaves over here through this analyzer, its intensity becomes I naught divided by 2 cos square of phi. This is law of Malus. It says that when an unpolarized light passes through a polarizer, its intensity becomes I naught by 2. Further, if it passes through an analyzer, second polarizer, which is placed at an angle phi with the axis of the previous polarizer, then its intensity becomes I naught by 2 cos square of phi. This is law of Malus. So can I say polarization or polarized light, if vibrations of electric field vector are limited in one direction, in a plane perpendicular to the direction of propagation of light, then the light is called plane polarized light. Yes, and the phenomena is called polarization. What does law of Malus say? Law of Malus says that light enters the polarizer, its intensity becomes I naught by 2. Okay. And then further, if it passes through the another polarizer called analyzer, its intensity becomes I naught by 2 cos square of phi. Let's suppose if the analyzer is placed at an angle of 60 degree. We say if phi is equal to 60 degree. Analyzer is placed at an angle of 60 degree. Can you check what is intensity? It will be I naught. Guys, what is the intensity? I naught by 2 cos square of theta. I naught by 2 cos square of 60. Cos 60 is 1 by 2. So I will become I naught divided by 2. 1 by 2 whole square is 1 by 4. 4 into his intensity will become I naught by 8. Okay. If I say theta is equal to or phi is equal to 90 degrees. Okay. Phi is equal to 90 degrees means you have completely tilted this at an angle of 90. In that case, let's check what will be the intensity. I is equal to I naught by 2 cos square of 90. Cos 90 is 0. I will come out to be I naught by 2 into 0. That will be 0. In that case, no light will pass. Intensity becomes 0 means no light will pass. Is this clear? Is this clear? Yes. Last topic is what we call the polarization by reflection or Brevister's law. See guys, what does Brevister's law actually say? See, we say according to Brevister's law, if an unpolarized light goes from one medium to another, we say this is medium 1 and this is medium 2. Okay. Brevister's law says that if a light goes from one medium to another medium, if a light goes from one medium to another medium. Okay, this is the last topic. 5 minutes it will take. We are done with the chapter. What dinner break? Already I have given you the break at 7 o'clock. We say if the light goes from one medium to the another medium, okay, my dear friends, we say some part of it gets reflected and some gets refracted. If you have got the two medias over here, medium 1, medium 2, air, and this is the medium U. When light falls over here, some part of it gets reflected, some part of it gets refracted. If light is reflected in the same medium, it is called reflection. If light goes into the another medium, it is called refraction. Okay? And then further. And if the angle between reflected light and refracted light is 90 degrees, if the angle between this reflected light and this refracted light is 90 degrees, if it came out to be 90 degrees, then reflected light gets completely polarized. This reflected light gets completely polarized. Okay, and refracted ray or light gets partially polarized. This gets completely polarized and this gets partially polarized. What does Brevister's law say? If a light is falling on a surface, above the surface you have medium 1, you have medium 2. Some part of it gets reflected, some gets refracted. If angle between these two came out to be 90, then this gets completely polarized. Polarization already we are done with. Okay, like here light, guys, in this particular case, see, take a look. This light over here, this dot means this is the electric field which is vibrating in Z axis. This means electric field is vibrating in this direction also. This direction, Z in this. So electric field of this unpolarized light is vibrating in two directions, like this and outside inside. When some part of it gets reflected, we say this reflected light gets completely polarized. Here see, only Z portion of the electric field is present over here. Here electric field is vibrating in the Z direction only. So this is completely polarized. And in this case, you see, this is partially polarized. Electric field here is vibrating in this direction, X as well as Z, X as well as Z. So this is partially polarized. This is completely polarized, this is partially polarized. This is what does the Brevister's law actually say. Okay. And incident angle is called the angle of polarization or polarization angle. This incident angle is called the angle of polarization at which this light falls. Okay. And we say this tan of angle of polarization is equal to mu. Mu is the refractive index of the medium. Okay. Mu is the refractive index of this medium in which light is refracted. Let's suppose if somebody says if the value of mu is √3, what is the value of angle of polarization? Tan IP is equal to √p. IP will come out to be 60 degrees. Okay. With this, we are done with the chapter. Thank you so much. Wave optics done and dusted. Let me know in the comments how was the session once I end the session. Okay. Thank you. Okay. Take care, guys. Huh? See you guys in the next session. So thank you so much. This was all about it. Take care. Take a chill pill. I would want you guys to let me know in the comments later on how was the session. And if you have not liked the session yet, I would want you guys to smash the like button as soon as possible. Okay. So do let me know in the comments how was it. And the next session, I'm going to take the class 11th. Class 11th is the next. And we say basic mathematics and vectors. 2 chapters I'll be finishing. Basic mathematics and vectors. Basic mathematics and vectors. Okay. Okay. And when it comes to the semiconductors, I'll be taking that also in the upcoming time. But as of now, I'll be starting the class 11. That is very much important because I have been receiving a lot of comments in every single session of mine. So please start the class 11th. When are you going to start? Please teach, please teach. I'll be taking that. So take a chill pill. You don't have to worry about anything. Okay. That's my job. I'll do that for sure. Okay. And by the end of this month, we'll get done with half of the, by the end of the next month, we'll get done, we say half of the 11th portion. Okay, that's for sure. And rest of the chapters we'll see also. Okay. So what else do you want? Anything else do you guys have to say? Anything else do you guys have to say? Let me know in the chats. Everyone means everyone. Okay. My pet. WB. Wasim Butt, huh? He's nowadays a gym freak, huh? He goes to the gym every single day. He's a disciplined person. He has become very disciplined. And he goes to the gym every single day, takes a protein, whey protein, and proper diet. Okay. He is focusing on his physique right now. Nowadays, I must say. Okay. Yeah. So thank you so much, guys. Take care. Take a chill pill. See you guys very soon. Thank you.